everyone, welcome to the Physics Chronicles. As I said, I am going to start from Fourier series, and this lecture series will contain the videos of mathematical physics, and simultaneously I will be uploading videos based on classical mechanics or quantum mechanics or electromagnetic theory. Right. So to learn this Fourier series, we must know what is this periodic function. So to apply this Fourier series, we can say to apply this Fourier series, the function must be periodic one. So the periodic function, you know that a function which gets repeated, periodic function, so a function which gets repeated after equal time interval, that is f of t plus capital T is equal to f of t plus 2 capital T and so on. So here this capital T is called time period of this function f of t. Time period, right? So these periodic functions are of two types. One is sinusoidal and another one is non-sinusoidal. Let's take the sinusoidal first. Sinusoidal. So the functions which are in the terms of sine or cosine, that are called sinusoidal periodic functions. Okay, so examples will be like sine x, sine t, cos t, or sine 2t, cos 2t, like this. Simply, if you want to plot this sine t, then this curve becomes something like this. And this is the one period circle, so this is called t. This is the time period. And here is the maximum amplitude A. This is minus A. This is A sine t. And its variation with time t, right? So this is the sinusoidal time period. Now there are some you may be asked in some exams, find out the time period of some sinusoidal functions. That is very important. So be careful while I am explaining this part to you. So if a function is given like this, sin mt or cos mt, remember its time period is t is equal to 2 pi by m, because these functions are in the terms of cos omega t or sin omega t, and you know if cos omega t or sin omega t is given, the time period is 2 pi by omega, right? And here in place of omega there is m. That's why we are writing the time period as 2 pi by m. And then let me take an example here. If you are given sin square t and it is asking its time period, then you can write it down as half into 1 minus cos 2t. If you open the bracket, then this will be 1 by 2 minus 1 by 2 into cos 2t. This is a constant, so the time period of this function will give you the time period of sin square t. And you know its time period is 2 pi by 2, that is equal to pi. So the time period of sin square t will be pi. Then again take second example, that is sin qt. And from the formula of sin 3t, you can derive the sin qt, that will be equal to 3 by 4 sin t minus 1 by 4 sin 3t. Now you have two terms, and both of them contains this sinusoidal function. So for sin t, you know time period will be 2 pi, and for sin 3t, time period will be 2 pi by 3. Now the problem arises. If one part has time period 2 pi and another part has time period 2 pi by 3, then what is the final time period of this sin qt? Remember this method. So you have to find out the minimum time after which both the functions get repeated. So for sin t, you have time period that is 2 pi, and this function sin t will be repeated after the time 2 pi, 4 pi, 6 pi and so on, right? And for the second part, this sin 2t, let me take this one time t1, this is t2, this is equal to 2 pi by 3. So this sin 3t will be repeated after 2 pi by 3, 4 pi by 3, then 6 pi by 3, and that is equal to 2 pi, right? You can clearly see after what is the minimum time. for sin t there is 2 pi, and for sin 3t there is also 2 pi. So this is the minimum time after which both sin t and sin 3t gets repeated, right? So the final time period will be 2 pi. 2 pi. So we can conclude one point here. The functions cosine or sine function having odd power, sine or cos, cosine having odd power have time period t is equal to 2 pi. This is the conclusion, right? Now let's go to non-sinusoidal periodic functions. So in case of non-sinusoidal periodic functions, the functions are not in the form of sine or cos, but they get repeated after a certain time interval. If you recollect, some of the non-sinusoidal functions are, if you see this rectangular wave or square wave forms, these are called the non-sinusoidal periodic functions. This is non-sinusoidal periodic function. If you see the square wave, then you can clearly see in square wave this width and this width are equal. If this is W1, this is W2, then we can write W1 is equal to W2. This is called square waveform. In electronics, you must have encountered this type of graphs, square waveform. This is a periodic function because after this time interval t, the function again gets repeated, but this is not in the form of sine or cos. That is the difference. Now second one, if you take rectangular wave, then in rectangular wave this width will be different. Here. Okay, so this is W1, this is W2. In this case, W1 is not equal to W2. This is called rectangular wave. Right? And some more examples you want to learn, you can see here. There is another kind of that is called triangular and sawtooth. In triangular, the waveform is in the form of triangles, like this. Okay, if you see, the time period is from this point to this point. This is time. This is called triangular waveform. Triangular waveform. Okay, and the fourth one is sawtooth. We will encounter all these things in Fourier series. I will do some examples. It looks like tooth, isn't it? And here we have some slow positive ramp and sharp decay here. Again slow positive ramp, sharp decay here. So this is the time period. This is called sawtooth type of waveform. So these all are non-sinusoidal type of periodic functions. So what is the significance of this Fourier series in these periodic functions? So what Fourier series does is we can convert these non-sinusoidal periodic functions. So these are all non-sinusoidal type of periodic functions. So what we can do, we can use this Fourier series to convert all these non-sinusoidal periodic functions in terms of sine or cosine. That is the main advantage of this chapter. Right? So let's see how we can do that. So here you have f of x, a non-sinusoidal periodic function. You can write this non-sinusoidal periodic function as summation over n from 0 to infinite an cos nx plus summation over n is equal to 0 to infinite bn sin nx. Now, by seeing this, you must have a doubt. That is, while writing the Fourier series expansion, you here write a constant and then we write these terms. है ना? So basic difference, if you see carefully, I have taken this limit from 0 to infinite, not 1 to infinite. In those cases, you take these limits from 1 to infinite and take a constant term. You can see here, if you put n is equal to 0 in this term, this will be a naught, this will give you 1, cos 0 is 1. Then you can take out this constant term. Okay, so basic difference is I am taking the limit from 0 to infinite. Right, so here what we can say that there is a set of functions. The set of functions, if you put various values of n here, you get that. If you put n is equal to 0, then you get 1 here. 1. Then if you put n is equal to 1, then you get cos x and so on, cos 2x. Similarly, if you put n is equal to 0, you get 0. We don't count that. And then you get sin x. Sin x, sin 2x and so on. This is the set we get. And this set represents an orthonormal basis. Orthonormal basis set. Okay, why orthonormal? Let me take an example. I will tell the equivalent example, then I will show you how these are orthonormal. If you study this quantum mechanics, there you tell this orthonormal basis sets, because the product of a function with that function, and again if you take the integral from some limit in some interval, then that will give you 1. You call that normalized. But when you multiply different functions and take the integral, that will give you 0. Let's see here. Two conditions are there. I am taking in the vector, you must have encountered this set I, J, K. Right? This is an orthonormal basis. Orthonormal basis. Why? If you multiply I with I, or J with J, or K with K, you get 1. This is the normalization condition, or normalized. If you we call it normalized. Then if you multiply I into J, or J into K, or K into I, similarly J into I, or K into J, or I into K, that gives you 0. This condition is called orthogonality. These are orthogonal. So this I, J, K are normalized and orthogonal to each other. That's why we call it an orthogonal basis set. Right? Similarly, this is also called an orthonormal basis set. How? You will see in quantum mechanics we do the integration. Here also we will prove this by integration. In Fourier series, okay, so I have taken in this previous, here I have written some formula. In that case, I have taken the integral from 0 to 2 pi. That's why I am getting cos nx or sin nx. Okay, here I am writing the general formula. So for in general, the interval will be a to b. Remember, I will be doing all the formulations by taking the general case. The advantage of doing all these things in general case, because in exam any interval you have been given, you can simply put a is something, b is something. After that you will find all the formulas or all the functions. That will be easier for you. So that's why I am doing in general. So if this is AB, interval is AB, then the set will be, the orthonormal set will be 1 cos 2 pi nx divided by b minus a, then cos 4 pi nx divided by b minus a. Similarly, sin 2 pi nx divided by b minus a, and sin 4 pi nx divided by b minus a, and so on. This is the orthonormal basis set. Okay, so let me show you that how this previous formula I have written. I have taken a as 0, b as 2 pi, or a as minus pi, or b is equal to pi. If you take this, b minus a becomes 2 pi, because 2 pi minus 0 will be 2 pi, and pi minus of minus pi, that will be also 2 pi. So 2 pi gets cancelled, we get cos nx, sin nx, and so on. That's why I have written the previous formula by taking the interval from 0 to 2 pi. Now I am doing it for general case. Now first one, if I take the integral a to b, then I can write down cos 2 pi mx by b minus a into cos 2 pi nx divided by b minus a dx is equal to integral over a to b sin 2 pi mx divided by b minus a sin 2 pi nx divided by b minus a dx. That gives you 1 by 2 b minus a delta mn. You know the value of delta mn. Let me write down here. Value of delta mn is equal to 1 when m is equal to n, and this is equal to 0 when m is not equal to n. This is the value of delta mn. Now if you see, okay, I have taken the same, the different functions here. Let's say m and n. This depends on m and n. Just carefully watch what I am saying. I told you in quantum mechanics, if you multiply same function, then integrate it over some interval, then this value, if gives you 1, then this form is normalized. Okay. So here, see, I have taken cos 2 pi mx or cos 2 pi nx. If m and n are different, in case m and n are different, then here you get some different value, delta mn, and here m and n are different. In different case, this will be 0. So I told you the condition of normalized, that will be equal to non-zero if normalized, and for orthogonal, if they are in two different states, that will be 0. So if m and n are different, then they are two different states, and their integral becomes 0. I told you, right? Same case will be for sine. Here two different states will be there, m and n will be different, this will be 0. If m and n are equal, then this will give you 1, and there will be some finite value. Then we can tell that these functions are normalized, right? Then let's see, I took cos and sine. Then let's take, this is an orthonormal set, so this should be, this condition orthogonal or normalization should be true for all the member of this orthonormal set. So let me take a product of a cos function and a sine function. So the integral is a to b cos 2 pi mx divided by b minus a and sine 2 pi nx divided by b minus a dx. This is always 0. These two are different functions, and this gives you always 0. Remember these integrals. This will be helpful after some classes. While doing integration, you will face some trouble. In those cases, this will help you. I am not just showing that these are orthonormal sets. I am just giving you some important formulas also. The third function, so we took cos function with cos function, sine function with sine functions in the first formula, and in second formula we took cos function with sine function here. Now only one possibility remains, that is 1 is also there. So this should also satisfy the orthonormal condition, orthogonal condition and normalization condition. Now let's take that condition. A to b 1 into cos 2 pi mx divided by b minus a dx, or integral over a to b 1 into sine 2 pi mx divided by b minus a dx is equal to 0. This is also true. Right? So let's take another possibility is there, 1 with 1. So if you take 1 into 1, then this will be 1 and dx will be simply b minus a. That will give you finite value. So if you see 1 with cos x is also 0, 1 with sin x is also 0. So now that is proved that the set of functions we get from this Fourier series is orthonormal set. Okay, so that's it for today. We'll meet in the next class and in the next class we'll calculate these constants, that is a naught or b naught or a n, all the constants we'll calculate. And don't worry about the figures I have drawn in case of non-sinusoidal periodic function. I will solve some of the examples. You will get the idea how we are doing it. And there are some complicated problems in your books also, that is the addition of 1 by 2 square plus 1 by 3 square like this. You must be afraid of those problems. You can solve it very easily. Okay, so don't worry, we will meet in the next class and we will take some examples also. See you in the next class. Stay home, stay safe. Bye bye.